This is a production of Cornell University.
So we'll go through this. I'm going to try to go, why are we doing this? Some of the history, how this all got going, and what's going on right now. And finally, I'll talk a little bit about how this is being done, the kind of techniques, so that when you see the map, you say, well, how are these people making these maps nowadays? So why do we do global mapping? And so the reason I'm saying this, we have now global models. There's a lot of global modeling, and I gave a good example here of a very popular model. There's a lot of demand for global assessments. So sea stocks, status of the world soil resources, where you're trying to compare countries, approaches, and so forth. And so you want some consistent global databases. And it has to be, of course, spatially explicit, because you would like now not only to have something, let's say, country by country. You'd like to really know where things are happening. So you'd like to have a global mapping effort. So why not combine national maps? That's be the obvious thing. We have a lot of countries in the world. And I'm talking now specifically about soil mapping, soil resource mapping. Many areas are not mapped at all. People have hardly been there. Large areas of the world, maybe a little bit of reconnaissance, but actually no systematic mapping. They're actually not very well understood, that at any scale they're not mapped. Many other are with poor quality maps. There are countries where there have been mapping programs, but the Soil Survey Organization has fallen into disrepair. The maps might be very old and done with poor techniques, poor georeference. Many areas don't have the key properties. So for your model, you might want bulk density. You might want carbon stock. You might want the salinity, something about salinity, and it's not there in that database. So even when you have the map of that area, you don't have the key property that you're interested in for your model. And finally, if you look at the national maps, obviously there's huge inconsistencies in methods that are used for survey, definitions, mapping standards, and so forth. And this is this is well known. And so we had a case a number of years ago. It was a very interesting case between the Netherlands and Germany, which are both very well mapped countries. And they did a project where this was maybe already 30 or 40 years ago. They took an area where part is in the Netherlands, part is in Germany, and the surveyors from the Dutch did both areas, and the surveyors from Germany did both areas, and both maps were published. And you see both are highly experienced mappers, but the maps look very different. Now, if you would go and use them for practical purposes, they'd probably be okay, but you can't just stitch those maps together, and they prove that with that program, and that's with two very highly developed and competent soil survey organizations. This is an example of what happens when the FAO tries to stitch together national maps. Now, the FAO, the Food and Agricultural Organization, has the mandate to work with countries. And so they like to work with each country, which makes perfect sense. And so they like to do their projects from the bottom up. And here we have two countries, and we're looking at their soil organic carbon stock. And which two countries are we looking at here? Oh, Canada.
Oh.
Can you speak?
Oh.
Can you sing "Oh, Canada"?
I could in two languages.
So this is our, these are our Canadian friends up here that seem to have a lot of carbon going on here. And here we have the line, here we are in Montana, and we look like we completely depleted our resources. Now, I'm not exactly sure that's true. Are the Canadian prairie farmers so much better farmers than our plains farmers in America? I'm asking you, Tony.
I would say yes, but
Yeah, but not
who am I to say?
But, and now let's go over to Asia. So we have a bunch of countries here. What countries are we seeing here? Parts of countries.
Like India.
Yeah, there, India's this part.
Nepal.
Nepal is here. Come on, you guys.
Bangladesh.
Bangladesh. It's the only one that knows anything, and therefore.
Pakistan and Afghanistan.
Bhutan, right? So not only are there big differences, but seriously, Bhutan apparently has done some kind of soil mapping project where they're showing a lot of detail. And you can see here in this, at least this part of India, in this project, I should say, this is what you get. So this is the problem with trying to deal with stitched together maps. So that's why we're thinking we want global products. This also calls a little bit in question if you would use a national product, is it how reliable? So what happened? Back in 1961, and a lot of you were not born back then, back in Cold War days, there was a lot of tension between the Soviet bloc and the Western bloc, but they managed to get together and an amazing version of what we call pedopolitics, pedo for pedology, for soils. A project was done by the FAO to make a soil map of the world involving the scientists from all the continents in a very collaborative project. So this was done at a scale of 1 to 5 million, which they felt was possible with the soil knowledge they had. This was very broadly defined soil classes, but at least it was somewhat useful. And back in 1986, Zobler digitized this, and for many years, this was your soil map of the world, a digital soil map with raster cells of ½ degree. And that's the only thing that was available, but it was a really good initiative. And this is an example of a map. They've all been scanned. They're all online and available, which I linked before. And I won't make you pick the countries up here, but this is the Great Lakes area. And here we have Lake Victoria. So we have Uganda, Kenya, Rwanda, Burundi, and over here we have DRC and South Sudan. And what you could see was the major difference in the detail that was available. Now, Kenya had a very active soil survey. Uganda, where the Katina concept was developed, actually. And with the Rwanda and Burundi, I have a special connection because my PhD professor here, Armand van Mabeki, and he's a Belgian, and when he was a young scientist in the late 1940s, these were Belgian protectorates, and he did the soil surveys of Rwanda and Burundi when he was, before he came here. He was my PhD professor then later in the 1980s. He had many good stories to tell about this. Together, the two countries are about the size of the Netherlands. But you see the inconsistencies, and also you look at some of these lines, they're obviously just guesses. Now, there's some knowledge there. So that was the first one. This is an idea of the soil legend, and they were just these overall classes based on soil genesis, and they had subclasses. This was fairly general map. This has been digitized and available here as we shape files and so forth. They have now actually gone and digitized that map, so they're not being updated, but you can get that if you want. Then the next big initiative was the Harmonized World Soil Database. This was between FAO and IASA, which is the Institute for Systems Analysis in Vienna, and with the place I work in the Netherlands now, ISRIC, World Soil Information, Chinese Academy of Sciences, and JRC. And this now is about equivalent more or less to 150,000 scale. It's a 30 degree. In this case, they said, well, we're going to just make the soil in 2 layers. There's the top and the subsoil. We have some, but the difference here was finally we had a map of soil properties. There's some estimates in these grid cells of the soil property values, and you can see the kind of things they have. This is a list of their properties. This is what it looks like in good part of the world. Let's see if anyone can identify where this is. Oh, you see it. So this is 19 here. This is in the PRC. And these are the soil type codes. You can see they have a soil type. And then you can then go to those and get something like topsoil sand proportion. So you get not a bad map at this resolution. Unfortunately, not every part of the world participated. And one group that did not participate was the NRCS in the United States. The map of the United States, I was embarrassed to show. New York State shows in 2 colors. They sort of have, and they have this line between the Appalachian Plateau and the Ontario Plain that kind of goes like this. So, yeah, they just didn't cooperate. The Americans are very inward looking. I say the Americans, I'm Dutch, so. Anyway,
No, but this is a good resource where it is. And what I just found out just last week, and I haven't had a chance to yet evaluate this, but the version 2 was just released, and they now have 7 layers instead of 2. They have very new data sources. They've added some properties here, especially things like CN ratio, aluminum saturation, that can really be really useful. And so the idea here, you can see it's objective. So global agri-ecological zoning. So this should be nice. I haven't yet evaluated it. These were done from legacy products, expert knowledge, and so forth, not the digital soil mapping techniques I'll talk about later. Then there was a project which was a challenge from our own Pedro Sanchez. Many of you may know him, a Cornell graduate, and then moved up in the world and has the World Prize at some point. And he challenged us in 2008. I'm speaking of the soil mapping community, and he's a soil fertility management person, but he said, look, I want these soil maps that I can go. Well, he said, I want to go anywhere in Malawi on any farmer's field, and you tell me my fertilizer recommendation. He said, well, dream on. This is not going to happen, but we can do better. They got the Gates Foundation and Jeffrey Sachs got involved, so the Gates got involved here. The idea was to have regional nodes working to one standard, and then they would put it together with, since there would be one standard, we would have one map. The standards were successfully developed, and these are now very widely used also in national parks. However, the project failed totally because they never thought it would be impossible to make regional nodes. North America worked well. By this time, NRCS was in the game and got interested in digital soil mapping. And so already had good relations with our colleagues in Mexico and Canada. And so North America was all right. South America, more or less, but in South Asia, no country is going to let their data go to one of the other countries. And the same thing happened in East Asia. So this failed as a project, but it had a good output, which were these specifications that were worked on quite extensively. And so if you're going to make it a digital soil mapping now, and have these specifications, they've been thought out a lot. They're very easy to use. And I wanted to show some results for the nodes that did work, so you get an idea of how this product will look. Here is Australia. And these are some properties. Let's see what I have. Sand, silt, clay, and what is this last one? I can't see what D is, but look at that. So this is all of Australia, sand, silt, and clay. And a very important factor here that was part of this standard that is now possible with the digital soil mapping techniques we're using is that you get an uncertainty map at the same time as part of the various techniques we use for the soil mapping. And these are, in this case, is on a relative scale expressed as a range of the 90% confident intervals standardized by the mean. So it essentially says, what's the width of that interval divided by the mean? And you can see some areas, in this case, of sand with very low uncertainty. But over here, in Queensland and in New South Wales, we have some higher uncertainty, and we also see higher uncertainty for silt and clay. So it's very useful because what you can now do is say which parts of the map are not useful enough for me. I can decide on a level of certainty. This is also useful for going out and taking more samples because presumably these areas that are not so well represented in your models, you have more information from there, the model will be better. So that's a little bit of history. So let's talk about who's now making global soil maps. Now, I retired from the University of Twente in the Netherlands because we have forced retirement in the Netherlands, unlike at Cornell, you can just go on forever and ever, feel like it. And so then they very kindly invited me to come here and continue my
Scholarship.
Thank you. But also in Israel, in Wageningen in the Netherlands, which is associated with the agricultural university, but not part of it, is an independent foundation that is the World Data Center for Soils. And this was set up pretty much at the same time that the FAO had the project for the world, the map, soil map of the world in the 1960s. And the Dutch government, the Ministry of Foreign Affairs gives the core funding for it. The idea with core funding for this gives the idea is to provide soil data for the world, and you can look at this. And we have a harmonized point database. So the idea is to collect points from all the countries you can get them from in whatever form these point data sets were given to you, and then harmonize them the best we can, put them in a database that's publicly available that people can use for their own projects. Some data we get under the condition that it can't be shared outside. So unfortunately, you can't see it, but we can use it for internal mapping projects. With that, we are making a product called Soil Grids, which I'll show in a minute, which is a global soil extent map. So it's a consistent map over the whole world, using as the basis our harmonized point soil database. And if you have any point databases you'd like to contribute, feel free. I was sent by the FAO to Cambodia a few years ago to evaluate a project that was done, and I went out to the ag experiment station, and I was talking with the soil scientist, and he said, yeah, the Australians were here some time ago, and they made this database, and I don't know anything about it, but here's the disk. No one's ever used it. So I took it back, and I looked at it, and so we wrote a memorandum. I said, this is great. They had done like 850 points all over Cambodia, all georeferenced, all analyzed. I don't know whatever happened to it in Cambodia, but anyway, we wrote a memorandum of understanding to the Ministry of Agriculture, and they said, sure, you can use this freely. We took it back. It's now part of our database. So that's the kind of thing you can do on your travels. Come across soil point databases, please let us know. So this is our idea: consistent point data plus covariates, which are environmental factors. I'll show you how that works in a minute. We get consistent global maps. And this is our little data model here. We have our data providers. It was a data model. We have our database that we can use for soil grids, and we have some various services, online services, so you can get all this stuff. Just wanted to show the kind of data we have. So if you look here, this is Central Africa, and you can see there's a lot of work in Rwanda. We have a lot of access. These are publicly available. So there's over 1,000 soil profiles you can get from this right, georeferenced in Rwanda. Burundi, hardly any, and that they're almost the same size. And of course, you can see the size of Congo. Other countries, there are more. We can't use all of it, but you can see the difference in precision that you might have. Here is in Europe, which is really, so don't think this only has to do with the countries with weaker soil organizations. Here we have our Belgians, and especially our Swiss friends are doing a tremendous amount of work, and the French are all on strike or something. And they're giving us, no, actually, the reason for that is the French have this very strong privacy laws that the location of the soil sample cannot be given out to the public, which is very different in the United States, where you can go, under the law as it now stands, the soil surveyors go out, take a sample, give the georeference, and it's publicly available. That goes back since President Lincoln set up the USDA with the idea that it would all be public. I guess you all knew that President Lincoln set up the USDA, started the Transcontinental Railroad. And there was something else he did, but I can't remember quite what that was now. something else important. Anyway, but seriously, they have a lot of points. So the French themselves can make these very good maps where we can't do that. So this is the problem with these sorts of things. So our product is this. We're using the global soil map specifications, and the concept of how big will the pixel size be is a contentious one. With the computer power we have now, you can make the map 10 meters, 20 meters, but do we have the data to support it? And we feel that this is actually really pressing it, even go to this level because of the quantity of data in the world. Now, our covariates, based on say remote sensing and elevation models and so forth, we have those at finer resolution, but to make the map, we're not confident. So we get 5 physical properties, 4 chemical properties. And we also were working on this world, WRB is the World Reference Base for Soil Classification, which is the FAO system, the international system now. Soil taxonomy is used in the United States and in some other countries like Venezuela, Thailand, and India, but the world system is used internationally. But that was an older product, and we are having a lot of trouble making these maps of the categories. So the methods we use, these random forests, which I'll show in a minute, they work well for the continuous properties, but for these classified properties with 32 classes and many subclasses, we have not had a lot of success, but we had one in a previous version. We have an outdated version that at least look at. We generalize these products because many modelers want a more general product, a land surface modeler. They're not going to look at something at a 250 meter scale. They're going to probably want a bigger scale. So we can easily generalize those. And it's available in Google Earth Engine catalog. And next week, my lucky students in the 6200 course will be using these layers out of Google Earth Engine. So this is a picture, and something about this, we can't see the country border. This is our friends in Canada. Here we are in Montana. Okay, here we have the Glacier Park, and you notice there's no border at all here. It's one model for the whole world. So, you know, this is good, and you can see a much more consistent picture here. So, you know, we go farther north, we're getting more stocks. We're getting more stocks in the higher mountains, for example, here in the Rockies and so forth. You know, when you get the lower ones in the plains and so forth, I'm not saying it's all correct, but we now have a consistent map. So if you were doing some modeling in this area between the two countries that are divided by just the parallel, then you would have a much more consistent product. We also have, this is a little hard for you to see here, we also have the uncertainty map in the same way that I showed you for the Australians. So in fact, the uncertainty is higher here in some of these areas. Even within the plain area, we have some areas with a higher uncertainty. This comes out of the mapping process, which I'll explain in a minute. And this is something I had a little fun with. I took all the soil properties and all the depths, and I did I just did some Kmeans clustering. And I said, well, do I see any natural soil units coming out? This is a map of our lovely area here, and I'm showing I did then the principal components of this, and I'm showing these natural clusters, and you know, it doesn't look all that bad. You know, we see the endless mountains down here. We have the Ontario Plain. Here we are in Aurora. You can even see our lower level kind of lake-derived soils here. So that was pretty interesting. So this map was made from a global map. So it used all the data in the world to map everywhere in the world. And all I did was take this part out that covers this area and do the Kmeans clustering and get this thing out of it. So if you're going in, so one of my take-home messages, if you're going to a new area that hasn't been mapped, you don't have a good soil map, you could do this. I think I put this on my website. I have to remember the technique. It's all in R, of course. And you get at least an idea of kind of the general zoning of your area according to the soil properties. So I thought this was actually pretty good. This was using Google Earth Engine. And the white is because we don't map in the city, in the water, or in the urban areas, urban area maps. Another provider I want to mention is FAO Soil Resources, because they are, as I said, an internationally mandated group to work on this. There's a structure called the Global Soil Partnership, and this has several aspects. It's a cooperative effort, bringing in all the different countries with a technical panel on soils. They have priorities for different years of the soils, do many things, as well as mapping. And the head of this is now was my master's student back there in the Netherlands, a Bolivian guy, Ronald Vargas. He's moved his way up over the years. So, and you can go to any of the big meetings, you'll probably meet him. They stitch together products, but I want to mention this, even though I told you that stitch products were not I have my problems with them because they do show the whole world, and it is another approach to mapping the world. And here's an example, again with US and Canada, of what they call black soils. This was a fairly controversial product. And they said, well, where are their definition of black soils is not chemnozems and it's not mollisols. It's a more general definition of what they mean by black soils. But then they decided they wanted to make a map because of all the interest in carbon. So they did this, and again, here we have the parallel, right? 49th parallel is right here between Canada and the US. You realize, Tony, we wanted 54-40 or fight, you know, you hear about that? We just gave up.
Yeah.
I don't know what to do. But anyway, this is their product, and so they are making products. So that's what I wanted to point out, more thematic products like this. Then here is some colleagues of mine that really have a tremendous work. Unfortunately, these websites are offline right now. I wrote to the Shangguan, the guy, my contact, and I visited them in this group. They used to be, you can see from the BNU, they used to be at Beijing Normal University, and the whole group got recruited to Sun Yat-sen University in Guangzhou. And they have these very nice global data sets, especially for hydraulic and thermal parameters. I'm going to write them again, so will they'll come back online. Maybe they've changed the address. As a few weeks ago, it was working. And the Wei Shangguan is the main author there. So if you're working soil hydrology or land surface models where you want thermal properties of soil, they've done a lot of derived properties. So they say, you know, the thermal conductivity of the soil, that kind of thing. Obviously, these are going to be somewhat difficult products to make, but they're working on this, and it's all gridded, and it was freely available. It is freely available when the website is on. Then another group, yet another of my students, was Tom Hengel, who was my PhD student some years ago. He worked at ISRIC, and he was behind Soil Grids version 1, and then he left to form his own company. And they make mostly regional maps because of demand, and they work on contract, but they're very innovative in very sophisticated techniques they use to make these maps. And this is a map that was done as an Africa project, so I'll show this. And this is, for example, is extractable iron. That's the kind of product they make. They make models of 30 meters, which I really doubt. It shows a lot of detail, which I don't think is really there. But anyway, that's one of the players. And you'll see their products. They're also based in Aachen. They're sitting in Aachen. So those are the people that are making the global soil maps now. And now I apologize if one I don't know. Please let me know if you know about one that I don't know about. If you're curious, I'll later show you the portal I have where I try to collect all these things. If I missed one, I'd like to know about it for sure. So I'd like to take the last part here, 10 minutes or so, to talk about how are these maps being made now? When I see these maps, I mean, if I look, how was this map actually made? Obviously, they didn't go out to every 30-meter square in Central Africa and do this. So what was going on? One way is to take legacy maps. So maps that have been made by traditional methods showing polygons. And these, the FAO Soil Map of the world, HWSD, and in the United States, the Sergo product, this is the way they're made. Going from maps that have already been made and somehow transforming those by decide on the scale or resolution in a legend. You make a common legend and you digitize them and you do some kind of harmonization. And that's the way the harmonized world soil data is. So they had polygon lines, digitized them, figured out a common legend, correlated them, and then rasterized it finally at some scale they would want. You would then link this to a database, and the way you would do that is you would say, well, in this polygon, it's represented by this. So in the United States, we have the dominant soil series in a polygon. It's got an official series description with a list of properties. And this is an example from US. I just wanted to show the way these things might look. So here we have a soil map, and here we have the tri-county corner, the corner here by Portland, Hopkins, and Tioga County. Here we are, Hammond Hill here. And, you know, in each of these polygons, this was done by manual methods. We can click on a point there, we can get the representative soil profile, and from that representative profile, have some idea of what the properties are there. But those properties, of course, would be inside everywhere that's marked here with VVV would have the same properties. But these aren't one way to make maps. But in many areas, they don't have these kind of maps. You can do that. So the more common method now that's used very widely is a digital soil map. And the concept here is to go direct to digital. So we're going to make a digital map from the beginning, only knowing from our points. So this idea was kicking around the late 1990s and 2000s, and then codified in this very good paper that it really laid out the whole landscape by Alex McGrathie and Mendonça Santos, who's from Brazil, and Budiman Minase is also, he's Indonesian, but he's been a professor in Australia now. So she was on sabbatical in Australia. They worked this out. So what do? We have a georeferenced head-on observations. You've got to start with that. So you have points, and you know where they are. And then you have the attributes there. So when I add a point and I knew the soil attribute, I also know I can take remote sensing images, I can take climate maps, I can take elevation models and terrain derivatives, I can take, say, the night lights map to see how much human activity there is, can make a big stack of these things. And since I know those everywhere, from the point that I'm at, I just go stick a pin right through those, and I have any number of what we call covariates that we think relate to the soil property. And that's the concept. There are a couple of methods, and I guess I forgot, I should have put this up first. At a very small scale, like in a field scale, with lots of intense data in the field, like from a yield monitor or something like that, or very intense sampling in the field, you can use pure geostatistical methods such as kriging, but that's not applicable over large areas. So in general, we now use machine learning methods, random forests are quite used, but also some people use gradient boosting or vector machines or neural networks. They all work the same way. The idea here is that the covariates we pick to represent soil forming factors. So we know that temperature, just to take an example, has a large effect on the carbon budget, right? At real high temperatures or low temperatures, moisture, that kind of thing, position on the slope. Things that we know from soil survey and from our theory of soil formation should have some relation. Now, this is just an empirical relation. We're not making any kind of process model. So we make these empirical relations, and we then can build a random forest that goes from all these predictors to our training data and see. And then when we have a new point, we just go into our random forest and we run down our random forest and we make a prediction. Now, there are problems with this, which I'll mention in a minute, but this is, since we know the covariates of all the grid cells, once we build a model, at any grid cell we now go to, we know that covariate, and we can go down that and make a prediction. So that's the way these are now made. Now, why is it so popular? Well, it's easy, rapid, and cheap. You just need a big computer, and you can even use Google Earth Engine. You don't cost you anything or very little. Very easy to do. But what is important is we now have covariates that we think are well related to the soils. And one I like a lot are the gamma ray emissions, which unfortunately we don't have over the whole world. But Australia has these, and that's one of the reasons they can make such good maps. It turns out to be a lot of relation to soil properties. You have good training materials, so FAO has done some, ISRIC has done some. So a lot of the techniques have been worked out. There are R scripts and Google Earth Engine scripts and so forth. The FAO made a very nice project on this. They have a lot of good training material, so quite easy to get into this. And this is negative. This is why it's possible. You don't need to know anything. So you don't have to know anything about soil survey to do this. You don't have to have any feel for the landscape. You just do it. And that's why, but the advantage there is there's a lack of trained mappers, correlators, and quality control Many countries don't have an organization at all, or if they do, it's very underfunded. And so, you know, you don't really have an alternative. So that's one of the reasons it's popular. You can go into a country and then, as I said, underfunded or non-existent soil survey organizations. So, for example, in Nepal, the FAO did a training, and Nepal only had soil survey done in a few of its places, but they wanted the whole map of the country. Don't have the money to send people out and do surveys all over the place, but they still made a map. Now, how good is that map is another question. So that's one of the reasons it's so popular. I won't spend much time on this. We have our observations and our covariates. We put them in this big, what we call a regression matrix, and there's a lot of technical deals here that we go through the model fitting and the tuning and so forth, and we end up making the maps and the uncertainties. This is an example of the soil grids problem. I don't know if anyone recognizes this area. It's not too far from here. Any Pennsylvanians here? Yes, I know we have a Pennsylvania. Any idea where is this? I'll give you a hint. It's in Pennsylvania.
That's behind it, right?
This is Lock Haven, Pennsylvania here. Williamsport, Pennsylvania over here. So
Yeah, like Land's End area.
what?
Land's End. Pennsylvania, like
That would be up here higher. That's, yeah, you're right. That's going, so this is the Allegheny Plateau. And here we see the prediction of sand. And you see very high sand contents up here in these sandstones at the top of the Allegheny Plateau. So the soils form, they're quite sandy, right? You get down here, now these are the famous limestone valleys. This has actually got a great name. It's called the Nippenose Valley. And back in my master's at Penn State, I was doing wheat breeding and I had some trials. So it's a beautiful little valley. So you can see these have very high clay content, very low sand. So it's not bad, but look at these things up here. There's definitely some artifacts. I mean, this is not right. There's no way that all of a sudden, I mean, I know this area. There's no sandstone outcrop or something that's making this area, this little one square with this really high amount, right? So that's not right. So you see the problem. We're doing this mechanically, but all in all, it's all right. So the model uncertainty, I mentioned this. And so I'll just point out that you could refuse to map areas that are too uncertain if you would want to. And that's one of the big advantages of this. To show you how bad the uncertainty can be, this is for our area here. This is our prediction of pH. So soil grids, and remember, this is being done with models calibrated with data from the whole world, right? Not just from this area. So here's our pH. We have right down to about 4.5s here, 4s. Up here, we're around 7s. So I'm not so sure these areas up around the Portland area are much lower pH than the hills to the south. I'm not sure. I don't think so. I didn't check today, so we have a little problem. But this is not bad, right? We're looking at pHs around 6.87 in Aurora. We're looking at, in our plateaus here, 5s. And so, but the uncertainty, the 5% quantile in the random forest is giving us values of 3.5 here. Don't drink that water. and then up in Aurora, really, way low. And look, here we have saline soils. We have pHs above 8 up in Aurora. No, can't happen. This is what happens with these models when you run it through the trees. This is what you get. So we publicize these so you can decide. And here's an area you think you see the pattern, but so the quantile, the uncertainty with the predictors we have is fairly high. Okay, last thing is how you get these things. I have a site that I maintained for many years. First, I was at the University of Twente, and then I moved it to ISRIC when I went there. I have all the world databases, everything we have, everything done by all the global coverages of other portals, and I have all the national data. So if you're looking for national data, you say, hey, I'm going off to Cambodia, what do I have? Please go look at my site. It's broken down by everywhere in the world. It's got other any soils data that I think is online. Every 3 months, I update this. So what are the issues? Okay, So you're here and you want to use global soil maps. Well, as I said, poor accuracy and high uncertainty. So the fact of the matter is there's a lot we don't know about the soil cover, right? So we unless you're in do a really detailed survey, these maps they give you an idea, it's better than nothing. But even in, so we have that wide incomplete distribution of points in feature space, meaning there are areas of the world that environments, let me say, that we've hardly sampled or that we don't have the data available. Some combination of environmental factors where we haven't gone and seen that data. The calibration points can be incompatible or outdated. They can be in the wrong place. So I had this happen to me when I went to Uganda once and went to the farm there, and the Americans had gone there and taken a few points that were in our database back in the 1980s before Bill Clinton turned off the selective availability on the GPS. So I navigated to the points, and this is, by the way, this is the exact place where the Katina concept was developed by Mill in the 1930s. With this beautiful regular landscape in the Kampala area in Uganda. And this very regular landscape, you have the parts of the soil forming a chain called the Katina. So I'm standing there and I said, this can't be right. And we went down to the village and we found the retired technician, who was quite an old man by this point, who had worked with the Americans when they were there. I said, can you take us to the site? He said, sure. So he said, okay, they were here. And as soon as I stand there, I say, definitely this is correct. I can see from the soil description, this is the right site. So I corrected the 4 GPS points. I took the proper GPS points. I went back to the Netherlands and we corrected them in the database. That's 4 points of the many thousands and thousands that are off. It was off by about 200 meters because the GPS was not so accurate back then. And you were in a completely different position in this beautiful hillside Katina. So it's, if I try now to correlate it with the elevation, the slope, or whatever, I'm in the wrong place. So my model is going to be bad because the soil is not where it's supposed to be. So that's one of our big problems. And we're now working on the derived properties of soil functions. So these are the future developments. What we really want, we want more covariates that are more related to soil formation. And we'd really like to now work on properties that are more useful directly to you. So instead of saying sand, silt, and clay, what's the hydraulic conductivity? What's the thermal conductivity? I was mentioning the work that was done in Sun University. And then the idea of communicating uncertainty, we'd like to be better at telling. People don't like uncertainty, but we want to tell them you probably shouldn't use this map, or depending on what your purpose is. So that's it. Thanks for your attention.
Very much, David. So we might have time for 1 or 2 questions. Yeah. So I think this is better as well. So I will actually repeat the question.
Okay, I'll cover.
Okay. It's a wonderful talk. I'd like to thank you very much for providing those products. My lab have used several of your products from HWSD and also soil grade and also the WOSES.
And WOSES, okay.
Yeah. So toward the end, you talked about the uncertainties and those, the important issue and you are addressing. And you mentioned that probably we need more data, more complete information. Besides that, are there other ways to address that uncertainty issue? If I understand correctly, your soil grid 2.0, after you use machine learning, R squared gets to like 0.64, is that right?
Well, it depends on each. So the question is how accurate is the overall R squared or accuracy? But that's per property. So each property will have a different one. They're in that rate. Yes, you're right. They're
soil
in that range.
Yeah, still like 36% of the variability cannot be explained. And do we have a way to to understand those variability?
Right. Well, the question is how can we reduce the error, and what are the methods? One point is I mentioned if Some of that error, remember, that's a global average of the error. So some areas might be predicted better than other areas. Some of that number is coming from areas we predict very badly because we don't have any representation of that place in the feature space. So for example, we had very few in the polar environments, in the circumpolar environments. So we were getting a lot of uncertainty there because that combination of the temperature, precipitation, frost periods, and everything else, we didn't have soils points that represented that environment. That's one. The other one is getting, and here's where I am working on, we are very poor at representing certain soil forming factors. And the most obvious one is time. Soils form over time. And there's a famous area in southern Germany that has got tropical soils. They're relic tertiary soils in this area near Munich that you would never predict from the current temperature and conditions there. And we have paleosols that are exhumed. Iowa is famous for this. You have previous glaciation soils that were weathered and are now we have nothing that helps us really get the time. So I don't know what covariates we might use. So that's, I think, where we're missing things. And then I'd say that's one of the main things that we are trying to improve covariates. I don't think the machine learning methods are the limitation. I think with better covariates and better data, then the machine learning would not be the limitation. Although you can always try to improve a little bit. That's not the main one. So thanks for the question. Yeah, Emily?
Yeah, I have a question about how current remote sensing products and maybe future remote sensing products are helping inform covariates, particularly with land cover. Although at the same time, we know that the time series behind those products is so short, but how have they been leveraged, and where do you see some new developments coming in that space?
Yeah, the question is, with the remote sensing products, we have more and more. How would they be leveraged? You make a very good point. Actually, we now have a longer time series. So for things like agricultural land or land that's managed, you have a 20-year time series that has not been exploited too well to try, for example, things like carbon, things like bulk density. If you could somehow relate that then but you would then need the soil observations at those different times. So that's what we haven't tried yet. There is a lot more precision in these, but yeah, I think some of the sensors there, my colleague, I should have put her name here, Laura Poggio is our main digital soil mapper at district, and she's actively looking for these new covariates, and the new remote sensing products are part of that. But yeah, the time series is quite interesting. I don't know how to say more than that.
Good to end. Yeah.
Well, wait, one
Last question.
Yeah, yeah, you. Because I know Joseph can talk to me later.
There are some level 4 products that are looking at biodiversity derived from spectroscopic imagers like G, and then we get spectroscopic spaceborne imagers like SPG. The existing one of the ISS.
Yeah.
If you know the species or at least the biodiversity, those then be data points to like calibrate the models that you have here in the soil. Like,
Yeah.
For example, some plants have very strict requirements on types of soil to grow. We have a pretty good understanding on the, at least in California, the range that, for example, agave has in California. If you know agave is there,
Yeah, no,
can you make assumptions?
that's a really good point. So the question was, could we, two things. One was about the satellite spectroscopy. So let me answer that one first. We use lab spectroscopy now routinely, and there is a lot of relational, but it's only the topsoil. That could, if we really get those, we can now start using some of the models we've calibrated in the lab with soil properties. That might really be helpful for certain things in the soil if we get the spectroscopy, the satellite spectroscopy. Second one is if we knew the land cover, the biotype, and I hadn't thought of that. That's a really good idea because if you see different land covers will have really big influences on the soil properties. Around here we have the famous red pine plantations that were put up by the CCC to recover farmland, but they acidify the soil horribly. They kill everything around it. And if you say there's a red pine plantation, your pH is going to be, I don't know how low, but you would make that correlation. That's a really nice point. Thanks for bringing that up. I'm going to think some more about that.
This has been a production of Cornell University, on the web at cornell.edu.